everybody. I'm sorry I'm not here today. We're going to pick up right where we left off, though. So if you would get out your note sheets, and we are on the back side of number 59. So please go to the back of page 59. And remember, we did already problems 2A and B. So we're just going to jump in and start with C. Now let's go back to the beginning of the problem and make sure we're clear on what the situation. We are going to be dealt a 5-card hand. Every single one of the problems in this string, A, B, C, D, E, F, G, H, and I, all deal with probability of being dealt a 5-card hand. Remember that probability is a fraction. So your probability for each of these problems is going to be something over 52C5, because probability is what you want over the total. And the total number of 5-card hands in a standard deck is 52C5. So every one of these problems on this whole page is going to be over 52C5. All right, so now I'm going to look at problem C. I want all face cards. All right, so I'm going to write that like this. I'm going to write P, all face cards. Okay, this is problem C. I already know the answer is going to be something over 52C5. Because if you're going to be dealt a 5-card hand, your denominator is going to be 52C5, because that's the total number of 5-card hands there are in the deck. Now, my numerator is what I want, which is all face cards. So I got to stop here a minute and think. How many face cards are there in the deck? If I split my deck into 2 piles and put all the face cards in this pile and everything else over here, how many face cards would there be? Well, stop and think. You have 4 suits. Clubs, spades, hearts, and diamonds. Each suit has a king, a queen, and a jack. So there are 12 face cards. 3 face cards in every suit. So my numerator is 12C5. 12C5. Now remember yesterday when we did one of these, I think it was problem B, we got a number in scientific notation. Please be ready for that to happen again. So I'm going to type in 12C5 divided by 52C5. And the answer is 3.047 times 10 to the negative 4th. Feel free to leave it in scientific notation or change it to its regular form, which would be, 0.000347. Good. Let's try the next one. What is the probability of being dealt all red? Okay, so this is the probability of all red. Once again, probability is a fraction. It's always going to be a fraction, a decimal or a percent. But when you calculate it, you will start off as a fraction. So we want the probability of all red. It's a 5-card hand. Our denominator is 52C5. Now what's our numerator? Well, split your deck into 2 piles. Here's your deck of cards. Split it up. Put all the red cards in this pile and everything else in this pile. How many cards would be in the red pile? 26. So your numerator is 26C5. You are being dealt all red. You want 5 red cards. Let's type that in and see what we get. That's going to be a little bit bigger number. Still not as big as you probably think. So 26C5 divided by 52 C5. 0.0253. So you can leave that as a decimal. If you'd like to change that to a percent, you can. That would be 2.53%. So there's about a 2.5% chance that if you are dealt 5 cards from a standard deck, they will be all red. E. What is the probability of being dealt a hand with 3 jacks and 2 kings? So E is what's the probability of 3 jacks and 2 kings? All right, once again, it's a 5-card hand. So my denominator is going to be 52C5. That isn't going to change. But now in my numerator, I want to get 3 jacks. So I'm going to split my deck up into those piles again, and I'm going to put all the jacks right here. How many jacks are there in the deck? 4. So I want to pick 3 jacks from 4. So 4C3. There are 4 jacks in the pile. I need to pick 3 of them. 4C3. I need 2 kings. Now I got a pile of kings right here. How many are in that pile? 4. And I want 2 of those. So 4C3 is my jacks. 4C2 is my kings. Here we go. This is going to be another really small number. Oops, better turn it on. Oh boy, 9.2345 times 10 to the negative 6th. Feel free to leave it in scientific notation. Please understand that is a really, really, really small number. Really small. So your probability of getting 3 jacks and 2 kings is not very good. I wouldn't bet my allowance on it. F. What's the probability of being dealt a hand with no face cards? So F is the probability of no face cards. It's a fraction. Probability is a fraction. What's our denominator going to be? Oh, please tell me you're saying 52C5, because that's always our denominator when we are picking 5 cards out of 52. That was my numerator. Remember a little while ago, we did a face card problem. We said we're going to split our deck into 2 pieces. We're going to put all the face cards here and all the other cards over here. Well, then I was picking from the face cards. This time I'm picking from the other pile. I don't want any face cards. So how many face cards did we say there were? 12. So how many not face cards are there? How many other cards are there? 40. So this numerator is 40C5. Once again, there are 52 cards in the deck. 12 of them have faces on them, jacks, queens, and kings. If we take out those 12, then we have 40 cards that aren't face cards, and I want to pick 5 of them. I want no face cards. All 5, no faces. So 40C5 is my numerator. This is going to be a bigger number. .2532, which if you want to say 25.32%, that's fine, or you can leave it as a decimal, 0.2532. So there's about a 25% chance that if you're dealt 5 cards, you won't have any face cards. G. What's the probability of getting being dealt a 5-card hand and getting all of the aces? Now, it doesn't say getting all aces. That would be impossible. You can't get 5 aces. It says you get all of the aces. So we want, for problem G, we want the probability of 4 aces and 1 other card. That's what's happening in this problem. It is a 5-card hand. We want all the aces. There are 4 of those. We're going to get them all. But then we need another card to get 5 cards. Your denominator is 52C5. You're sick of me saying it. I'm sick of saying it. It's a 52. There are 52 cards in the deck. It's a 5-card hand. Your denominator is going to be 52C5. Your numerator, now wait here, I want 4 aces and 1 other card. Okay, now let's think about this for a second. How many aces are there in the deck? 4. And we want all 4 of them. So that would be 4C4 for the aces. But that's not enough. You need 5 cards. So you got to pick up another card. Well, how many other cards are there to choose from? Here are the 4 aces. We've taken them out. How many other cards can I choose from? If you said 48, you're right. There's 48 other cards, and I need to choose one of those 48. That will give me 5 cards in my hand. The 4 aces, and then the extra card that comes from the pile that's not aces. Now, do you see this and right here? We talked about this yesterday. It's 4 aces and 1 other card. Whenever you see the word and, what operation? Multiply. I am not going to type any more of these into my calculator. We've practiced enough. I think you're able to do that, and I don't want to waste class time, video time on that. So this would be the setup. Excuse me. You're going to type this in on your calculator and get whatever decimal you get. H. We want 2 10s. I'm going to go ahead and write it. And 2 jacks and 1 queen. So we're very, very specific. A 5-card hand. We want 2 10s, 2 jacks, and 1 queen. What's our denominator? Hey, at this point, you had better be saying 52C5 because we have 52 cards in the deck and we're choosing 5 of them in a 5-card hand. So the total number of ways we can do that is 52C5. Now what's our numerator? Oh boy, we got to pick 2 10s. How many 10s are there to pick from? 4, 1 in each suit, you're right. So that's going to be 4C2. There are 4 10s, I'm going to choose 2. How about jacks? I want 2 jacks. Same thing, you're right, 4C2. 1 queen, I need 1 queen. What's that look like? 4C1. There are 4 queens in the deck, and I'm going to pick one of them. Any one. Now what do I do with these 3 numbers? Here's my 2 10s, my 2 jacks, and my 1 queen. What do I do with those 3 numbers? If you said multiply, you are right. Because what's the key word in the problem? 2 10s, and 2 jacks, and 1 queen. And whenever we say the word and, it means we're going to multiply. That's the fundamental counting principle, and it means we're going to multiply. So you're going to type that in on your calculator, and you're going to get a decimal. And you can just write down the decimal, and it probably will come out in scientific notation, so feel free to leave it in scientific notation. And finally, I. What is the probability, this is problem I, what is the probability of being dealt no aces and no queens and no fives. Now, do not make this harder than it is. I want you to think about this for a minute. Here's your deck of cards. Let's take out everything we don't want. So let's take out the aces. So how many cards would that be? 4. So I'm going to take out the 4 aces. Subtract them. Get them out of the deck. We don't want them. We don't want any queens. So we're going to take out the queens. How many queens are there? There's 4 of those too. No fives. I don't want any fives in this hand. So I'm going to take out the fives. How many of those are there? 4. So here's my deck of cards, and I have taken out the aces, the queens, and the fives. They're out. How many cards are left? Well, how many were there to start with? 52. And I just pulled out 4 and 4 and 4. So how many cards are left in my hand? 40. I'm going to pick 5 of those 40 cards. That is the setup to the answer. You're going to take that into your calculator and get a decimal. That one will be bigger. If you want to write it as a percentage, go ahead, or you can leave it as a decimal. It's completely up to you. Either is perfectly acceptable. One more thing to talk about, and then I'll set you loose on your homework. We're going to go to page 60 of our note sheet, page 60, and we're going to look at Venn diagrams. Now, you have all seen Venn diagrams in your life. I don't know how comfortable you are with them, and since I can't talk to you about it today, I'm just going to kind of assume that you don't know anything about them, and we're going to start from the beginning. So let's take a look at this Venn diagram that we're starting with. I'm on page 60 of my note sheets, and I expect each of you to be there with me. Here is the Venn diagram. Now the problem isn't really stated. You are told, okay, that this box contains 30 students. You are told that there are 30 students in the class. And apparently, the teacher has done a survey and asked the kids, do you like M&Ms? Do you like Twix? And apparently, there were 6 kids, these 6 right here, who what? Liked both. So when the teacher said to the class, who likes M&Ms? These guys raised their hands. And when the teacher said who likes Twix, they also raised their hands. These kids are in the overlap of the M&M circle and the Twix circle. That means they like both. Now there's 11 kids out here. Now what are those 11? What are they? Well, they're kids that when the teacher said, do you like M&Ms, they raised their hand. But when the teacher said, do you like Twix, they didn't raise their hand. These guys like only M&Ms. These are M&Ms only. They are not part of the Twix. These guys are M&Ms only. And what about these 9? These 9 are kids that when the teacher said, do you like Twix, they raised their hand. But when the teacher said, do you like M&Ms, they did not raise their hand. These 9 like only Twix. Now here's something I need you to understand. There are 11 kids that like M&Ms only. There are 6 kids that like both. And there are 9 kids that like Twix only. Okay, wait a second. How many kids is that? How many kids are represented in these circles? Add them up. That's 26. So wait a second, wait a second, wait a second. How many kids are in the class? 30. Wait a minute, that's only 26. Where are the other 4? The other 4 are out here. They don't don't like any candy. When the teacher said to the class, do you like M&Ms? They did not raise their hand. When she said, do you like Twix? They did not raise their hand. I don't know what's wrong with them. I personally like candy. They don't. They don't like candy. So you've got 11 liking M&Ms, 6 liking both, 9 liking Twix, and 4 liking nothing. That represents your 30 kids. So now we can answer the questions. How many students like M&Ms? Now wait a second. It doesn't say like M&Ms only. It says how many kids raised their hand when the teacher said, do you like M&Ms? How many kids raised their hand when the teacher said, do you like M&Ms? 17. 17 students like M&Ms. So the answer to A is 17. B says only M&Ms. How many like only M&Ms? That's the 11. Remember, if you are in the M&M circle, you like M&Ms. So there are a total of 17 kids inside the M&M circle. But only 11 of them like only M&Ms. How many like M&Ms and Twix? Well, that's easy. We talked about it. That's the overlap. That's the kids that are part of both circles. How many like M&Ms or Twix? You already know the answer to that question. We already figured it out. 26. How's come there's 26 that like one or the other? Well, there's 11 that like M&Ms only. There's 6 that like both, and there's 9 that like Twix only. So how many kids in this class raised their hand once or twice when the teacher said, do you like this candy? You see how there were 26 kids who raised their hand? There's 26 candy eaters in this class. E. How many like only M&Ms or only Twix? Okay, now wait a second. How many like only M&Ms? You know that. How many like only M&Ms? 11. How many like only Twix? 9. Now it's like only M&Ms or like only Twix. We talked about that yesterday. The word or tells you you're going to do what with those two answers? You're going to add them. So how many kids? You have the total number of kids that like M&Ms only or like Twix only. F. Already figured it out. How many don't like candy? In this class, how many don't like M&Ms or Twix? Those 4 that are hanging around out here. And again, we knew there were 4 because there's 30 altogether in the class, and there are only 26 represented in the circles. So that means the other 4 have to be out here. One more. I promise. This is it. Number 4. Now we're going to build our own Venn diagram. So let's see if we can here. What's going on in the problem? Everybody read it. Problem number 4. Now we're talking about a class of 28 students. I'll put 28 here to remind me there's 28 kids in this box. And they either like jazz music, I'll put a J, or they like country music, or they like both. These would be the kids right here who like both. Draw a Venn diagram showing the following. How many students like only jazz? Now what's the given? 18 students like jazz and 14 students like country. All right, now this, you gotta put your thinking caps on. Here we go. I'm the teacher standing up here in front of this class. There's 28 kids in the class. I say, how many of you like jazz? And 18 hands go up. Okay, let's put your hands down. How many of you like country? 14 hands go up. Okay, wait a second. How many hands total went up? If 18 went up for jazz and 14 went up for country, there were a total of 32 hands that went up. So 32 hands were raised. What's wrong with that? Why does that concern me? Groupies, there's only 28 kids in the class. How is it possible that 32 hands went up if there's only 28 kids in the class? Somebody raised his hand more than once. In fact, how many people raised their hands more than once? 4. There are 4 kids that raised their hands twice. Because there are only 28 students in the class and 32 hands went up. So 4 people had to have voted twice, which is fine. They're the people that like both. Now, remember that when I said how many people like jazz, there were a total of 18 hands that went up. 18 people raised their hands. Now, 4 of them also raised their hands for country. How many then only raised their hands for jazz? 14. The total J ball, the total J circle is 18 people. As soon as we figured out that 4 of them were in this little football here, there have to be 14 out there. Similarly, there were 14 students that said they liked country. 14 said they liked country. That means the whole C circle is 14. But 4 of them are in the football park. So how many of them are just out here? 10. So in this problem, we have 14 people who like only jazz. We have 4 people who like both. And we have 10 people who like only country. How many is that? That's 28. Notice, that's everybody. But notice that the problem says each of the 28 students in the class either likes jazz, country, or both. That means there aren't any out here. Everybody in the class is in a circle, one circle or the other or both. 4 kids were in both circles, 14 were in just this one, and 10 were in just this one. So now you can answer the question, how many students like only jazz? That's the question. We did all this work, I did all this blabbing to get to that question. How many students like only jazz? Only jazz would be 14. Okay, well, I'm not able to answer any homework questions right now at this moment. I'd like you to begin your homework right now. So tonight's homework, get online, see what it is. You may work individually, or you may work with your next door neighbor or with somebody else in the room. But please, everybody right now is working on math. Let's get as much of this done as we can, because whatever you don't finish is the homework for the weekend, because on Monday, I will expect to have this assignment done to the best of your ability. We will go over questions on Monday. Questions over this and questions over your homework. So, since it's Friday, and I'm not here to give you my Friday hug, I'm going to do it virtually. Here's your virtual hug. And remember to be safe and smart, make good choices, and I will see you on Monday.